someone inside the atom. In 1890, Lord Kelvin, the man who gives his name to the Kelvin scale, confidently predicted that all of physics would be solved in the next 10 to 20 years. That by the beginning of the 20th century, we'd have solved physics. There'd be nothing else to learn. This is because his conception of physics was simply the things that we encounter day to day, what we now refer to as Newtonian mechanics. This is the physics of balls falling, of water flowing, of tennis and cricket and things you can touch, normal things moving at normal speeds that we interact with as humans in our day-to-day life. They were learning about how gases could be heated up and cooled down, beginning to get an idea of electricity. Then, at the start of the 20th century, two new massive branches of physics were discovered. The first was special relativity, the physics of stuff that's going really, really fast. The second was quantum mechanics, the physics of stuff that's very, very small. Turns out that very, very small things don't act like pens and tennis balls. They act in completely different ways. And if you're going to understand modern physics, you have to understand the workings of these very tiny particles. Today, we're just going to be looking at the very basics. You've probably heard a lot of this before, but it's important that we talk about all of these things just so that we're all on the same page before we move on to the more advanced quantum mechanics. So, what's inside an atom? Well, there are three particles inside an atom: electrons, protons, and neutrons. Well, what do we know about them? Let's start with the electrons. They've got a negative charge of what we call -1. Now, that's not -1 coulomb. It's actually -1.6 times 10 to the -19 coulombs. But we say -1 because it just makes the math so much easier. So this is our unit charge. Electrons are also very, very, very small. They're 3 orders of magnitude, so 1,000 times smaller than both protons and neutrons. They have almost no mass at all. They're absolutely tiny. Next we have our friend the neutron, which has no charge at all. They're very, very boring. And finally, the proton, which, as we know, is positively charged. Now, interestingly, the neutron is ever so slightly heavier than the proton. Not so much that we normally take it into account, but when we're dealing with quantum particles, sometimes that becomes very important, a slight extra bit of mass. Now, as we'll learn when we talk about things decaying, everything always wants to decay to something with less mass, something lighter and more stable. So it actually turns out that protons are more stable than neutrons. If you leave a lot of neutrons alone for a very, very long time, they will eventually turn into protons. So these are our 3 particles which are inside our atoms: electrons, neutrons, and protons. And we write down our atoms like this. We'll write down the name of the element, symbol for that, so in this case, lithium. We'll write the number of protons here and the combined number of protons and neutrons here. This number here has a lot of different names, but the 2 we're going to use in physics are atomic number and proton number. The atomic number is the most important thing when you're considering an atom. All lithium in the universe has 3 protons, all of it, and it all acts like lithium. If you change the proton number, you change the element. Take one away, this will become helium. It will start acting like helium. It will be very, very different. This number here is the combined number of protons and neutrons. We call it the mass number, or often in physics, the nucleon number, where nucleon is just the combined word for protons and neutrons. It's both of them together. You're going to hear the word nucleon a lot. It just means a proton or a neutron, something inside a nucleus. We can change the number of neutrons in an atom without changing what element it is. As long as it's got 3 protons, it's going to remain lithium. So if we were to add or take away a neutron, it's not going to change the properties of that substance very much. It will still be lithium. We call these different numbers of neutrons isotopes. So an isotope is just an atom of a given element with not the number of neutrons you'd expect. Therefore, the mass number or the nucleon number may be a little different. The final thing you need to know when we're talking about these very, very basic terms right at the beginning is specific charge. Specific charge is defined as the charge of the atom divided by the mass of it, or the charge of the particle divided by the mass of the particle. You can use specific charge for anything. It's just charge divided by mass. If we think about specific charge of our neutron is going to be 0 because it has no charge. However, the specific charge of the electron is going to be massive compared to the specific charge of the proton, because although they've got the same magnitude of charge, the mass of the proton is far, far greater than the mass of the electron. Therefore, the specific charge of the proton is far, far less. Specific charge is useful because of our favorite equation in physics, F equals ma. Therefore, acceleration equals force over mass. When we're considering these charges, the force on them will be proportional to the charge. You increase the charge of something, and the main force we're dealing with is electrostatic, because gravity isn't going to affect these tiny particles very much. The force entirely comes from the charge part. So how particles accelerate will be a function of their specific charge. So if you had two particles, and one of them had double the charge and double the mass of the other one, they would both move the same way when we exert an electric field on them. So if we double the charge and we double the mass, the acceleration will stay the same. This is why specific charge is so important, because it's very easy to discover. Fire particles into an electric field or a magnetic field, and they'll move dependent on their specific charge, because it will be a function of both their charge and their mass. Nowadays, we know what the charge and mass of all these particles are, so lots and lots of experiments. But when we were just learning back at the start of the 20th century, we discovered a lot of specific charges. And that's really where the idea is important. If you want to understand the history of science, you need to get your head